All right, welcome. Today, we're going to dive into a set of ideas that are absolutely foundational for building software. We're talking about code that doesn't just work right now, but is actually built to last, built to evolve, and ready for whatever tomorrow throws at it.
So let's start with a question that, let's be honest, every developer has faced. You build something. It's clean, it's elegant, you're proud of it. But then, over time, with new features and bug fixes, it just decays. It becomes brittle, complex, and eventually a total nightmare to change. Why on earth does that happen?
Well, this thing actually has a name: software rot. It's this natural, almost inevitable degradation that happens to a codebase unless you are actively, and I mean actively, managing it for resilience. So how do we manage it?
To fight back against this rot, a set of 5 principles emerged over time, and together they give us a guiding philosophy for building software that's durable, adaptable, and a heck of a lot easier to work with.
Now, while the core concepts were developed by the legendary Robert C. Martin, you probably know him as Uncle Bob, it was actually Michael Feathers who, around 2004, came up with the super catchy acronym S.O.L.I.D. And that simple act, giving it a memorable name, helped these ideas spread like wildfire, becoming a bedrock for modern development.
So here they are, all 5 of them. Together, they form this amazing strategy for creating systems that are just, well, easier to understand, easier to maintain, and way easier to test and extend. So, let's start breaking them down, shall we?
All right, let's pop open this toolbox. We're going to look at each principle one by one to really see how they help us fight that software rot we were talking about. First up, we've got the S, the single responsibility principle. This is all about creating components, like classes, that are absolutely laser-focused on a single job. One job and one job only.
But here's the real nuance, and this is where a lot of people get it twisted. A responsibility or a reason to change isn't about how many methods are in your class. It's about the number of stakeholders, the number of different people or departments who might ask for change. If both the accounting team and the IT team can request changes to the same class, guess what? It has 2 responsibilities. And this example just nails it. Instead of one big, monolithic user report class that does everything, generates data, saves it, emails it, we segregate those concerns. We break it up. Now, a change to the email system doesn't risk breaking the core reporting logic. It's just so much safer.
Okay, next up is O for the open-closed principle. The goal here sounds a little like a paradox, but it's incredibly powerful. You should be able to add new features without ever changing existing, proven, working code.
This question right here is the heart and soul of this principle. Every time you modify production code, you introduce risk. You have to retest everything. But extending it, that's much, much safer.
So, instead of a brittle calculator that has a giant if-else block that needs to know about every single shape, we design it to work with any object that behaves like a shape, anything that fulfills a shape contract or interface. This makes our system endlessly extensible without ever cracking open that core calculator code again.
All right, on to L, the Liskov Substitution principle, or LSP. This one sounds a little academic, but it's really all about making our abstractions reliable. It's about maintaining behavioral correctness, making sure that a subtype doesn't cause unexpected, weird surprises for the code that uses it.
You've probably heard this famous duck test analogy for LSP. It's perfect. A subtype has to behave in a way that its parents' clients expect. It's not just about matching method names, it's about fulfilling the entire behavioral contract.
The classic square rectangle problem illustrates this perfectly. Look, code that uses a rectangle expects to be able to set the width and height independently. But a square subclass violates that core assumption. That means a square is not a substitutable rectangle, and trying to make it one breaks the principle.
Next, we have I for the interface segregation principle. This one's pretty simple. Stop creating these massive, fat interfaces that force clients to know about a bunch of methods they'll never, ever use. And here's the solution. By splitting a huge iWorker interface into smaller, more focused role interfaces like iWorkable and iFeedable, clients like our robot only need to care about the methods that are actually relevant to them. This creates systems that are way cleaner and much more decoupled. And finally, we get to D, the Dependency Inversion principle. This one is a big deal. It's arguably the most architecturally significant of all 5 because it dictates how we manage dependencies between our high-level business logic and our low-level details, like databases or file systems.
Now, here's the crucial point we have to clear up,
because it trips people up all the time. The dependency inversion principle, DIP, is not the same thing as dependency injection, DI. DIP is the architectural goal, the what and why of depending on abstractions. DI is just one common technique, the how, that helps us get there.
Okay, so it is so important to remember that these principles don't exist in a vacuum. They work together, they have this amazing synergy. But, and this is a big but, applying them also involves trade-offs that require some real professional judgment.
You can see how they reinforce each other in this beautiful flow, right? You create focus components with SRP and ISP. Then you use OCP and DIP to build a flexible system on top of them. And the whole time, LSP is acting like a quality check, making sure the whole thing stays reliable as it grows.
But look, S.O.L.I.D is not a silver bullet, and it definitely has its critics. These aren't rigid laws, they're condensed wisdom, and applying them effectively requires experience to find that sweet spot, that perfect balance between ideal, decoupled design and practical, readable code.
So what's the ultimate takeaway from all this? S.O.L.I.D isn't about dogmatically following a set of rules. It's really a discipline, a mindset for building software that can actually withstand the constant pressure of change. It encourages us to constantly ask ourselves, not just, hey, does it work right now? But a much more important question, is it prepared for what's coming next? And in our world, that is a question absolutely worth asking.